All right, guys, continuing with 6.3. This one here, we're going to talk about the mean and standard deviation of a binomial distribution. Okay, very, very easy stuff. The key is knowing that it's a binomial distribution. If you know it's a binomial distribution, this is going to be very easy. So if a count x has the binomial distribution with number of trials n and probability of success p, the mean and standard deviation are, to find the mean, it's n times p. Okay, can't get much easier than that. Standard deviation is the square root of n times p times 1 minus p. And that's it. Okay, that is it. So we're going to go back to that free throw example we did a little while back, where a basketball player, let's say it's 80. It's pretty close to what her percentage is. A basketball player makes 80% of her free throws. Okay? In a game, she takes 3 free throws. How many do we expect her to make? So we had that where she makes 0 and 1 and 2 and 3. Those are the possibilities, right? We had this as 0.008. This was 0.096. This is 0.384. This is 0.512. This is your random variable x, and this is the probability of each of those, okay? So we want to find how many we expect her to make. That's our expected value from 6.1. Okay, well, what do? We do the formula. U equals n times p. The number of free throws she takes is 3. The probability that she makes one is 0.8. And so when I do that, we expect her to make 2.4 free throws. Okay? We expect her to make 2.4 free throws. Probably should say when she takes 3. When she takes 3 free throws, we expect her to make 2.4. Okay? Now, let's do the standard deviation. Well, the standard deviation is just n times p times q, or n times p times 1 minus p. We take the square root of that. So that's going to be, let's see, what do we have? N is 3, right? Well, we just have that right there. 3 times 0.8 times 0.2. Okay, so 3 times 0.8 times 0.2. This is going to be 0.16 times 3, 0.48. So the square root of 0.48 equals, I've got 0.693. Okay, and so if I wanted to interpret that, when she takes 3 free throws, we expect her to make 2.4 free throws, and we expect that to vary by 0.693 free throws. Now, it doesn't really make that much sense. We're only taking 3, but that was the example that we used. Okay? Another example to look at. Okay, it says rolling doubles. So this is all chapter 6 stuff. Great to review it. Okay, so that's what we're doing here. We're reviewing it. They give you a probability distribution. Remember, to have a legitimate probability distribution, all the probabilities have to be between 0 and 1, and these probabilities have to add up to 1. Okay, in that case it does. We have a histogram. The histogram looks like this, which means it looks like it's a skewed right histogram. The mean they found is 0.667. The variance they show, and the standard deviation is 0.746. So just an example to look at, reviewing stuff from 6.1. Okay? Let's do an example. tastes as good as the real thing. The makers of a Diet Cola claim its taste is indistinguishable from the full-calorie version of the same cola. To investigate, an AP statistics student named Emily prepared small samples of each type of soda in identical cups. Sure, it beat. I'll make sure it's not my camera. Then she had volunteers taste each cola in a random order and try to identify which was the Diet Cola, which was the regular cola. Overall, 23 of the 30 made the correct identification. If we assume that the volunteers really couldn't tell the difference, then each one was guessing with a 1 out of 2 chance of being correct. Let X equal the number of volunteers who correctly identify the colas. Part A. Do this piece by piece here. Explain why it is a random variable, okay, a binomial random variable situation. So remember, to do that, we're using bins, okay? We're using bins, B-I-N-S, okay? Binomial, okay? They're guessing, okay? Either the cola, it's either cola or not cola. And that's their guess. There's two things. You either think it's the cola or you think it's not the cola. Independent. Each cup is, each person tasting is independent of the other. So that checks that off. And you could write that out there. Okay. Each person's guess is independent. Okay. Whether the first person guessed whether it was cola or not cola has no bearing on the other guesses. Number of trials, I think they said was 30. And the probability of success is 1.5, or 1/2. Okay, either you're right or you're wrong. Find the mean and standard deviation, interpret each value in context. Okay, here you go. Find the mean, find the standard deviation. Do it. Okay, so let's do it. N times P times Q. The mean is N, which is 30, times P, which is 1/2, times Q, which is 1/2. Right? N times P, oh, I'm sorry. No, my mistake. I was getting the standard deviation. N times P. Okay? N times P, that's our formula. 30 times 1/2 is 50. Standard deviation is N times P times Q. So 30 times 1/2 times 1/2, and then take the square root of that. So when we do that, 1/2 of 30 is 15, 1/2 of that is 7.5, and then we take the square root of that. It's going to be 2.74. Now we have to say it in context. So, remember, when we do this, we're talking about many, many times. It's an experiment, right? So if we did this experiment many, many times, okay, and the actual probability of getting one right is just 1/2, okay, then the correct number of guesses we would expect, okay? So if we did this experiment many, many times, okay, and the people were just randomly guessing. They were randomly guessing, okay? If we had 30 volunteers, we would expect to get around 15 correct guesses, and we expect that amount to differ by 2.74 correct guesses. Okay, so again, you talk about doing it in the long run. If you do this experiment over and over and over again, okay? and your N is 30, we're expecting that it should be about 15. The average amount they get it correct will be about 15. And we expect that number of 15 correct guesses to differ by 2.74 correct guesses. Okay, so that takes care of both of those things in one shot. All right, CYU, page 393. Go ahead. Oh, actually, wait, I didn't do the, I'm sorry. I forgot this last part. So part C says, of the 30 volunteers, 23 made correct identifications. Okay? Does this give convincing evidence that the volunteers can taste the difference? So again, we've got 30, right? 10, 15, 20, 25, 30. If 23 made the right guess, this is the way that they look at it, okay? If 23 made the right guess, they want to know how unusual that is, okay? Is that convincing evidence? Well, the way that they're going to look at that is if 23 or more people correctly guess that it was the right polo, is that convincing evidence that you can taste the difference? So they want to know the probability that X is greater than or equal to 23. That's just the way that they look at it. I don't know why they do it that way, okay? You know, some of you might say, well, why don't we just do 23? And I think that their reasoning behind that is it's not just 23, but it would be 23 or more. Is that unusual? So this is what they're looking for. So they want this. So how do I find that? Remember how we did that, okay? We can't find greater than or equal to using binom CDF. We have to use less than or equal to. So we're going to do the probability, or 1 minus the probability, that X is less than or equal to 22. We're going to go right before that. We're going to find this probability and subtract from 1. So you go to your calculator and you do the binom CDF. Okay, binom CDF. Let's see, so we go second dister, binom CDF, trials is 30, probability of correctness is 0.5, and then we're doing 22, 0.9974, 1 minus 0.9974. So if we do 1 minus that, 1 minus 0.9974, we're going to get 0.0026. 0.0026. That's the probability. Okay? So if it's true that people are just guessing, okay, that there's a 0.0026 chance that if you have 30 volunteers, 23 or more of those could guess correctly. So is that convincing evidence that they can taste the difference? What do we think? What do we think? How would we say that? It's such a small number, okay? So when the number's that small, we usually say that that's convincing evidence. Okay, let's see how the book worded it. There's a very small chance there'd be 23 or more correct guesses if the volunteers couldn't tell the difference. So if the volunteers were really guessing, if they were really just guessing, okay, there's a 0.0026 chance that 23 or more would guess correctly. So therefore, that's convincing evidence that maybe they can taste the difference. Okay? Maybe it's really not just a 1 in 2 chance. Okay, we're gonna question that, okay? Because the way that we did this was, if they were really guessing, if they really didn't know, there's only a 0.0026 chance of happening. That's a very small probability. So then you think there's something going on there. Okay, that's how the statistics work. You'll see that over and over again. All right. All right. Let's see what we got next. Let's turn the page. CYU, guys. There we go. Now you guys can do that CYU. Okay, now you can do the CYU. We're getting there. We're getting there. 6-3 is a long section, as you can tell by the pages and pages of notes. But we are getting there. All right, guys, so let's take a look. Let's take a look. Okay, we got that check your understanding, and I'll pull that up and answer some emails right now. I'm filming this, it's the last day before winter break, December 23rd. I'm gonna guess, when are we watching this? We are probably watching this the third week of January, that's my guess. Third week of January, we'll see if it comes true. All right. Check your understanding. I love these check your understandings. Gives you a good idea of exactly that, checking your understanding. So it says, refer to the previous check your understanding about Mrs. Desai's special multiple choice quiz on binomial distributions. We define x equals the number of Patty's correct guesses. So we're going to find the mean of x. Well, you need a little background information for this. We had to go back a little bit, right? So we have 10, I think there were 10 questions, and the probability of getting n equals 10, and the probability of getting it right on a guess is 0.2, because there are 5 choices. So 10 times 0.2, and that's going to be 2. Okay? So we have to interpret that, okay? So we would expect out of 10 multiple choice questions that we would guess correctly 2 times, okay? And that amount will vary by, let's do the standard deviation, 10 times P times Q. Okay, we do that out. Let's see what that is. It looks like I get 1.265. We expect the individual guesses to vary by 1.265 correct guesses from the mean, which was 2. Okay? Talk about the difference from the mean. What's the probability the number of Patty's correct guesses is more than 2 standard deviations above the mean? So that's a different question. That's an interesting question. I'm curious if you guys got that correct. So it's not more than 2 guesses. It's more than 2 standard deviations above the mean. So we have to find out what that is. So we're talking about this binomial distribution where you can get 0 right, you can get 5 right, you can get all 10 right. Now they said 2 standard deviations above the mean. Well, the mean was right here at 2. 1 standard deviation